Good morning, good afternoon, and good evening, everyone. So, today we're going to be continuing our statistical learning series, and we're going to proceed to chapter 2, and we'll see how far we can go from here. Okay, so let's just hop right into it. Okay, oops. Okay, is it recording? It keeps doing that. Anyways. Okay, so what is statistical learning? Obviously, that's the first thing they ask. Okay, in order to motivate our study of stat learning, we begin with a simple example. So suppose we are statistical consultants hired by a client to investigate association between advertising and sales of a product. The advertising dataset consists of the sales of that product in 200 different markets along with advertising budgets for the product in each of those markets for three different media. So that's the TV, the radio, and the newspaper. The data are displayed in figure 2.1. Where is that? Oh, here. And it is not possible for our client to directly increase sales of the product. On the other hand, they can control the advertising expenditure in each of the three media. If we Google what expenditure means, I think it's like how we spend or like a spending plan, the action of spending funds, the amount of money spent. So it's the amount of money spent in each of the three media. So therefore, if we determine that there is an association between advertising and sales, then we can instruct our client to adjust advertising budgets, which increases sales, right? So, okay, let's just dissect what we basically talked about. I'll go ahead and pull out my notebook here. Okay, I'll just do a new section. Chapter 2. Let me just go here. Oh, can't do that. Okay. Name. Okay, this is chapter 2, stat learning. I'm still trying to figure out how to organize these as I'm doing them. Okay, so here, what we basically talked about, am I trying the right screen? We're trying to define what exactly is statistical learning. And so we start with an example, right? So what is statistical learning? So to start with our example, right? Okay, so we want to, okay, let me just go here. Here's the example. So we want to explore, identify, analyze, learn. We want to analyze the association. When we say association, what does that mean? What's the relationship, right? So let's just say relationship. What's the relationship between advertising and sales of some product? So how do sales and advertising relate to each other? of some product. So it's this idea of relationship. Then the advertising data set consists of sales of that product in 200 different markets. So we have an advertising data set. It has sales of that particular product in 200 unique markets, and along with its advertising budgets for that product in each of those markets for three different media. So that's TV, radio, and newspaper. Okay, let me just go ahead and look at the screenshot here. And I will, for the figure, right? If we remember that figure, I'll go ahead and quickly copy and paste that thing. Oops. Okay. Okay. What what's the big idea here? Apparently our client cannot directly increase the sales of the product, right? There has to be some factor or something that's making our sales increase or decrease. And so we're going to look at advertising in order to identify that factor, right? But so here's the good thing about it. Even though we cannot or the client cannot increase the sales of that particular product, they can actually control the advertising expenditure. Meaning, how do they spend their advertising budget on TV, on radio, on newspaper, right? And so if we spend it on those three different media, then somehow there has to be some relationship or it has to somehow increase or decrease our sales depending on how we spend our advertising budget on those three media, right? And so that's something we can control. And so that's the idea. Wait, let me go back here. Okay, let me just go back here. Yes. So therefore, if we can determine, I'm right here, if we determine that there is some association between advertising and sales, we can then instruct our client to adjust the budgets, right? Which indirectly increase sales. So in other words, our goal is to develop an accurate model that can be used to predict sales based on the three media budgets. And so in this setting, the advertising budgets are input variables, while sales is the output variable. And so the input variables are typically denoted using the symbol X with a subscript to distinguish them. Subscript is the bottom one. So X sub 1 might be TV budget, X sub 2 is radio, X sub 3 is newspaper. So that's just a mathematical way of doing it. And the inputs go by different names. So one of them could be predictors, one of them could be independent variables or features, or just sometimes variables, right? The output variable, in this case, sales, is often called the response or dependent variable. So that's sort of like the output. Dependent meaning it depends on the budget, right? And so that's typically denoted using the symbol Y. Throughout this book, we will use all of these terms interchangeably. So they could be called predictors, independent variables, features, or sometimes just regular variables, and then output variable, response, dependent variable. And more generally, suppose that we observe a quantitative response, Y, and P, different predictors, or a number of predictors P, we assume that there is some relationship between Y and X. So that's just an assumption, a mathematical assumption that there might be some relationship based on the behavior of that data. And they can be written in this very general form. Now, I don't know why they put like an epsilon here. Okay, sure. Okay, so let me just go ahead and go back to my notes. I'm gonna quickly write that. Oh, wait. So that's the idea of this thing. So we want, wait, I already said that. We want to analyze the relationship between these two. And so one way of doing that is trying to determine some relationship. So how do we do that mathematically? So we want, or our goal is to find or develop model, some model to predict sales. So regardless of finding that relationship, well, that's the first thing we want to do. And then we want to make a model that's based on that relationship and it can be used to predict sales based on advertising budgets. So 3 media budgets in this case, right? Okay. So, mhm. So here we let x sub 1, x sub 2, x sub 3 be advertising budgets on sales, radio and news, or whoops, TV, radio, and newspaper. The TV, radio, and newspaper budget. And all of them are basically used for advertising the product in various markets. Okay, and then we're going to let Y be the output, or basically the sales, the number of sales. I'm assuming it's just number of sales. So what do we mean by that? Actually, no, I'm not gonna do the. Okay. So in general, it would probably look something like this. So let's say there is a correlation between those two, the predictors and the response. Then, oops, how do I, trying to think of a way to write this in an easy way. If there is some relationship of Y and we call them maybe P predictors. Depends on how many predictors we have. So in this case, we had 3 predictors in our example. So this one's going to be from x sub 1 all the way to x sub p. Those predictors. Then there has to be some relationship. Actually, let's just do this. Let's equate it to x, this whole thing. So it would look something like this. My y, which is just my, or some function. We plug in that x there. So that's the function we're going to be looking for, plus this epsilon, which if we go back, let me just double check. Is there a meaning to that epsilon? I had no idea there was some meaning to it. I'm just double checking, seeing if there's some meaning that we can relate to. I'm just charging. Okay. Wait, is there a meaning to this thing? Hmm. I don't know if I'm sharing the book or I'm sharing the. Wait, shoot. I think I'm sharing my notes. Okay, let me go back to sharing the book. And apparently, huh, where's the notation? Oh, there isn't like a notation thing, huh? That's funny. Okay, we went through that in our last video, which has been a while back. Okay, I can't seem to find it. Cool. Okay, let's just go ahead and go through it. So, okay, we stopped here. So that's the general form, right? Y equals some function where we plug in these predictors plus some epsilon. I'm just gonna assume that's noise, right? Actually, you know what? There's this thing called Google. I think it was like epsilon. Yes. What does that mean? Regression analysis. Oh, we call that an error term. So that's the outcome. This is the function that models the relationship between its predictors and the response. This function could be some linear polynomial or any other mathematical function. X is the predictors. And then this, yeah, I know it's an epsilon because I've seen it in calculus. I just didn't know what it was used for. But apparently, this is some error term. It accounts for the variability in y that is not explained by the function x. So it could be measurement errors, omitted variables, or inherent randomness in the process. Oh, okay. Let's just, yeah, let me go ahead and screenshot that thing. So we call that an epsilon. See, this is the reason why the textbook doesn't really explain everything. I'm going to go ahead and put that here. So that's what that epsilon's for. Okay, cool. Now going back to the book. So that's our data, right? On the TV, the radio, and the newspaper. And so the advertising data set, that's the advertising data set. And what does this tell us? This plot displays the number of sales in thousands of units. So these hollow red circles, they're basically sales, right? It's the output. Those are the sales. And it's some sort of function of the TV, the radio, and the newspaper in thousands of dollars for 200 different markets. So I think these should be a total of 200 if I added all of them. And each plot we showed the simple least squares fit of sales to that variable, as described in chapter 3. Okay. In other words, each blue line represents a simple model that can be used to predict sales using TV, radio, and newspaper. So based on this, we can actually kind of see that as we increase the budget for all of these, TV, radio, and newspaper, sales will increase, right? That's the idea. Okay. I'm just trying to see if I can. Wait, they should be 200, right? Yeah. That's something I'm also gonna, or we're gonna talk about it in some way or form. Yeah, I'm not super sure. We'll probably talk about it. Least squares fit, something I'm not sure of. Mm, we probably talked about it in some way, shape, or form. What's this? Linear regression. Oh, Python. Okay. Yeah. It's really just the idea where we can we go, oops, where am I going? 26. Okay. So that's the idea. And so in each plot, we show the simple least squares fit of sales to that variable, as described in Chapter 3. In other words, each blue line represents a simple model that could be used to predict sales using TV, radio, and newspaper, respectively. Here, f is some fixed but unknown function of x1 to xp. And epsilon is a random error term. Oh, there we go. They described it, which is independent of x and has mean 0. In this in this formulation, f represents the systematic information that x provides about y. So that's that idea, right? Okay. So it's really just like how we can relate x and y in a systematic way that's not all over the place. So here we can kind of understand using some mathematical function how we can relate x, the predictors towards its response. And so it's really just something like this, where you have like, let's say, years of education and then the income, and then we see this kind of trend of increasing. And we kind of just draw this blue line or this blue curve, this blue mathematical curve, which really tells us in a systematic way, this is how we can relate the years of education towards income. And I'm assuming that these data points, these red points, they're the number of students who have finished a certain number of years of education. And here we can see that the more education, well, more years of studying, of schooling, more income, right? Okay. Yeah, that's another thing I'm gonna put in my notes. So keep going to the chat for some reason. Okay, so here we have this epsilon, and this also means that it's a random error term, right? So another thing that we can say about this is a random error term. It takes into account those randomness that's not kind of part of or it's inconsistent. It helps us identify those outliers. Basically, those points that are not consistent with the data or the curve, right? Or maybe even deleted data that's not included in the graph, right? There could be something along the lines of that. And okay, what else did we say about it? It has a mean 0. When we say mean, it's the average of all of those. It has a mean 0. So it has a mean 0. And here we can use this as our example, the income data set and how that associates with the years of education. So okay. So here we can kind of see the red dots are the observed values of income. So these are in thousands of dollars. Years of education for 30 individuals. So I'm assuming that these are, if we count all of these red points, which I'm not going to do in this video, they should be 30, right? Okay. And then this right graph shows this blue curve, which represents some relationship between the income and the years of education. which is generally unknown, but it's known in this case because the data were simulated. And so the black lines represent the error associated with each observation. When we say error, we see how far is the actual value to the fitted curve, right? That's what that's basically telling us. And note that some errors are positive if the observation lies above, and some are negative. What do we mean by positive? This one, for instance, is positive, right? Because this one is oh, that's a very big, this one's above, while this one is below, right? Okay, that's too big because I zoomed in. But yeah, that's the, let's see if I can go back to the, okay, yeah. And some are negative. Oh, but overall, if we were to total all of these errors, these positive and negative errors, we divide them by the number of observed values we have, we should get zero. So that's what that is. Okay. As another example, consider the left-hand panel of figure 2.2. Okay, they talked about it. I'm going to skip that bit because they did talk about it. I'll go back to the book. Yes, they did talk about what we were talking about. So that's 30 individuals. Mhm. Income is a simulated data set. Blue curve, vertical lines. So yeah, the vertical lines represent the error terms epsilon, right? So 30 observations lie, some lie below it, some lie above it. And if you were to get their mean value, which means their average, so we just add all of them up, divide it by 30, or in general, the number of observed points, we should get zero. And in general, the function may involve more than one input variable or more than one predictor. And so in figure 2.3, two-dimensional surface, oh, it's talking about this thing, I think, or no, I think it's talking about something else. Oh, whoa, it went from here to, okay, anyway. So this function may involve more than one input variable. And in figure 2.3, we plot income as a function of years of education and seniority. So basically, okay, I don't know what seniority means in this case, but cool. Here, F is a two-dimensional surface that must be estimated based on observed data. Okay. In essence, stat learning refers to a set of approaches for estimating F. In this chapter, we outline some of the key theoretical concepts that arise in estimating F, as well as tools for evaluating the estimates obtained. Okay, so that's, in general, that's what stat learning is. So we've kind of went over it. So basically, stat learning, if we look at the definition, it's a set of approaches and these approaches helps us estimate the function. So because one of the questions we might be asking is, how in the world did we fit this, right? Because we could have done something like, I don't know, we could fit like that. Or funny enough, we could even do a straight line. But why a curve like that? We could fit it like that. Why does it have to be a curve like that? Why can't it be why can't it be like this? Why can't it be a logistic decay function, which is something, okay, it looks kind of similar. That's funny. Or a log function like that, right? I think that was ln of x or something like that. Yeah. It's one of those elementary functions in calculus. Why does it have to be a blue curve that's kind of kind of like shaped like a, I don't even know what that is, like a hump? And that's what we're gonna learn. What are these approaches or these techniques that we can use to estimate such a function? I don't know why I added question mark. And so we're gonna learn that throughout the book. And not only that, once we estimate f, how do we evaluate these estimates? So it's not just approaches for estimating f, we also have tools for evaluating. How can we be sure how accurate this estimation is? Stuff like that. Can we quantify certainty? Can we quantify probability? Okay, now I'm going into a new topic. So that's the idea. Maybe there's a way to do that. Maybe there's a mathematical reason why we choose this curve instead of another. Stuff like that. Which I find it pretty interesting to talk about. Okay. And so maybe before we get into the what and how do we do it, maybe let's get into the why. So it's actually a good segue here. 2 point was this 2.1.1. So we're asking here, why do we estimate f? What's the reason for doing that? Well, we want to predict data. Oh, there we go. That's one of the reasons there are two main reasons. One is prediction, one is inference, right? So one of them is prediction. Now, what do we mean by prediction? In many situations, a set of inputs X, so those predictors, are readily available, but the output Y cannot be easily obtained. Just like in our previous example, we can't really directly increase sales because that's not really the underlying reason or the underlying factor that's affecting that. So, but we have some things that we can control, which are the inputs. So the TV, the newspaper, I think it was the radio. There's an old textbook, a radio. Okay, so that's that, right? So how can we use that to predict? And so in this setting, since the error term averages to zero, we can predict y using this. Okay, let me just say this. So most of the time, we have input x. So that's like the radio, the TV, newspaper budget, right? We can control that. That's something that we can control. But we don't have y. And so that could be something like sales. But then we want to increase our sales. We want to increase y. So from this thing that we got here, so we can, if we don't have y, we can predict y. Or in this case, predict sales. Okay, I'm using the previous example. And we'll do it using a math notation here, which is, it's not going to be too complicated. It's going to be y. This arrow means it's not certain or it's not exact. And then some function as well. Then we put our predictors here. Yeah, so when we say there's a tilde, it means it's not accurate. Let me just go over what each of these are. So that F with the arrow, it's actually just an estimate. So yeah, see, I was right. I was thinking of something that's not accurate. So that's estimate for our actual F function. Y, let me just do it here, is the prediction. So again, it's a prediction, it's not accurate. So that's the prediction for Y. And so in this setting, oh, so this is where one of those issues of statistics come in. In my opinion, I think it's an issue. And I think it's also important to note. Okay, let me put this in, I'll put in red. I'll put in red. Maybe a note. So this is often a what we call a black box. Why do we say it's a black box? Because we don't know its exact form, right? We don't know its exact form, but it yields accurate predictions. So, in my terminology, because we can't understand it, so this is something we can't understand, but it works. Funny enough, it works. So it yields accurate predictions, but we can't understand how it works underneath the hood because it's not something like, okay, if you guys taken pre-calculus or calculus even, it's not some function like 2x where we can just predict exactly that, right? It's something that we cannot predict or we cannot understand how it works underneath the hood. So something like this is impossible. Or often, it really depends on the data, right? So we cannot fully understand how this works. But it does yield accurate predictions for Y. Okay, so I'm gonna go through some example. Suppose that x1 to xp are predictors, are characters. Oh, now we're going to contextualize this thing. Okay, how long is this? Okay, it is a pretty long. Oh, and then we get into the how part. How do we estimate these things? I like how this textbook is written because it really goes into, or at least for me, it goes into how I think. So first I'm asking, how do we do it? What is it? Why it works? So it really goes into the nitty-gritty stuff. Okay, it is a pretty long, yeah, this is a pretty long textbook, so I'm not gonna dive into it too much. But okay. Oh shoot, it is pretty long. Okay, I can't do all of chapter 2 in one go. Okay, that's something I cannot do. Whoa, yeah, it is a pretty long thing. Anyways, okay, let me go back to the. Oh, I went too far back. I think I was just 2 pages in. Okay, okay, let's go to the. Yeah, let's just go for the prediction part, and then we're done. At least we're done for this video, right? Because this is a pretty long textbook. So yeah, again, it's a black box that we can't really understand, but it works. It can accurately predict why. So just to contextualize what that means. So another example here. So here, okay, I'm gonna write it in a math way. Suppose x1 all the way to some xp. Those are the number of predictors. These are what we, let's say these are characteristics of some blood sample. Okay, now note I'm not a, I don't know what you call this, a biologist. So I don't really know what these characteristics are. I only know type 1, type O, type B. Okay, I'm gonna stop. Type A. So suppose there are characteristics of a blood sample, how red it is or something, and they can be easily measured in a lab. Y is, so Y is the predictor. So Y is, it says here, a variable encoding the patient's risk for a severe adverse reaction to a drug. So this is, Y is a patient risk to a drug. Now, I don't know how to quantify that thing. Risk, maybe like high or low. How risk to a drug, or like a probability to have a reaction to a drug. How do I write that? Y is to, oh, okay, to react to a drug. So what's the likelihood of this patient reacting to a drug? Will it cause them, I don't know, chicken pox or something? Or lipoma? I don't know what I'm saying. To a drug, some particular drug that we don't know. So those are so it's more like how we contextualize these things, right? So what we're going to do is we're going to predict what's the risk of that patient reacting to some drug based on the characteristics of that patient's blood sample. So that's what we're going to do. So in other words, we're going to predict Y based on X, right? So we're going to predict Y based on X, where X is X sub 1, oops, all the way to X sub B. I'm going to make it mathematically complicated. It's really just me. So predict. So if we want to contextualize it, predict risk of reaction to a drug based on blood or characteristics of the blood. Really, it's just that, right? That's the idea that we're going for. How can we predict its likelihood to have a react? It's how do we predict a patient's likelihood of reacting to a drug based on their blood characteristics? How do we do that? We'll get there, not in this video, maybe in the next one. So we can predict this using those predictors. And from there, we can then avoid giving the drug to that patient, right? And so, okay, we'll get, I really don't want to end the video because this is too exciting. I have to end it though because it's too long. So the accuracy of Y. Oh, so now here's where the prediction comes in. We're getting there, we're getting there. So if you want to predict Y, right? How what did we say? We're gonna use this thing. And so here's, oh, what am I doing? So if you want to predict, so that's the goal, predict Y. We're gonna use that Y with the arrow. So the accuracy of that Y with the arrow as a prediction for Y depends on two quantities, which we will call the reducible error and the irreducible error. right? So what does that mean? Let me just do this. So we're gonna test, we're gonna look, or we're gonna analyze the accuracy of this thing to predict. Why? Depends on two quantities. So the idea for predicting is we want to quantify two things, which are reducible error, which I'm assuming is can we reduce this error, and irreducible error. This is the error that we cannot reduce. I don't know. We'll find out why they're called that way. Reducible error. Oh, so yeah. So our function. So that's one more thing. This thing is not a perfect estimate to this thing. I'm putting approximate because it's not a perfect estimate to the exact function that we're looking for. And this inaccuracy will introduce some error, right? Just like in our previous example on the education and the years of education and the income, we had some errors that are above the fitted curve and below the fitted curve, right? And so we call that the error, that we call that the reducible error, because we can potentially improve the accuracy of F by using the most appropriate statistical learning technique to estimate F. So here we're going to be using more tools to perfectly, not really perfectly, to better estimate F, right? So when we say reducible error, this means we can improve this thing to achieve, or to not really achieve. We can, but we depends, to get close to this thing, to F, right? And we're going to use statistical learning techniques to do that, which we have yet to learn about. Anyways, however, even if it were possible to form a perfect estimate for F, even if we were to find that, so that our estimated response is exactly that, our prediction would still have some error in it because y is also a function of epsilon, which by definition cannot be predicted using our predictors. So in other words, this is the irreducible error, this epsilon, right? Since this is something that we cannot control, it's just there. It's the noise in the data, it's the outliers, it's the that type of stuff, right? Mathematically, that's not something we can solve, unfortunately, right? And so no matter how well we estimate F, we cannot reduce the error introduced by that epsilon T. Now, here's the question. Why is the irreducible error larger than zero? The quantity epsilon may contain unmeasured variables that are used in predicting y. Okay, that's interesting. Mhm. Since we don't measure them, F cannot use them for its prediction. Wait, let me. So this is something. So again, it's really all about control. This is something we can't control, and it just happens. This is something we can control. How can we better fit this approximated f to get close to its exact value, right? Okay, wait, I'm a bit confused on this part. I'm just gonna write it down, see if I get it. Why is the irreducible error something? So why is the irreducible error epsilon larger than zero? Is it though? Oh yeah, it is. It just has an average of zero, but why is it larger than zero? Oh, okay, now I get it. So the quantity epsilon may contain unmeasured variables. Maybe we omitted some data that may be useful in predicting our output or y, our response, since we don't measure them. We cannot measure the irreducible error. And so that means F cannot use them for its prediction. We'll get, yeah, I'm starting to get a bit, but we'll probably understand this a bit more through coding examples and stuff like that, which we'll get to in the future. And so that quantity epsilon may also contain unmeasurable variation. Oh, so that's what it means. This one contains unmeasurable variation. Now, what do I mean by unmeasurable variation in case it's still a bit confusing? We cannot measure variables. Maybe unmeasurable. What are variables we cannot measure? Name. What else? Brand of a restaurant. Brand of different restaurants. How do we measure that? That's categorical, right? We can only measure something with quantity, quantitative data, not categorical or qualitative data. Okay. So for example, the risk of an adverse reaction, so if we go back to the previous example, might vary for a given patient on a given day, depending on the manufacturing variation in the drug itself. Oh boy, I'm not gonna get deep into that. I can't really. Okay, maybe there might be zinc, calcium, and stuff like that. I don't even know. There might be some variety of chemicals that's in the drug. Maybe that's why there's a different reaction. Or the patient's general feeling of well being on that day. Maybe the patient's actually sick during that day, and that might affect the reaction. So there are a lot of unmeasurable variations or unmeasurable factors that we can't really control, right? It really depends on the person. There's a lot of factors behind it, and we cannot quantify everything. So, yeah. Okay, let's consider. Oh, yeah, speaking of the. Oops. Oh, wait, something that I think is important to go back to, because I don't know why the textbook wrote it this way, but basically, if we go back to that income and years of education, okay, maybe next time they show it or they introduce it, I'm just gonna put it there. Okay, let me. Oh, my bad. Let me actually put it here. Right here. Oh no, I put it down here, right? There you are. Okay, that's also something. So the plot displays the income as a function of the years and education, years of education, and seniority in the income dataset. So the blue surface represents the true underlying relationship between the income and the years, as well as the seniority, right? And then these are the data points. So if you were to go back to that example. I think they had like a discussion here. Ah, here we go. Here's the little here's a little thing that we might want to look at. There we go. So in general, this is a function of two variables actually. We can plot its income based on the years of education and seniority, right? So here we can combine two predictors to get some output. So this is like if we go back to our calculus, okay, maybe let's not introduce calculus here because it's too much. But let's say we had some, okay, I'm assuming you guys know pre-calc. I'm just gonna assume we have some input, we get some output, right? That's a function. But then we can also get some inputs here. And yeah, we have some inputs here and they lead to some output. And so that's the same thing, right? This one is gonna be some curve. I don't even know, some curve like that in 2D. But if we were to change this and maybe do something like this, well, then now we have a 3D thing. That's just the difference of this. Okay, I can't draw. Maybe like that ish, right? Something like that. So not everything is in 2D. Some could be in 3D, and then we have to take into account these predictors, right? That's how we can form it. And then those are the plots. Those are the yeah, that's the plot, the surface. And then these are the data points. Cool, cool, cool. Okay, now going back to the unmeasurable variation, the things that we cannot measure. So if we consider a given estimate, oh, let's actually write these. So let's say we have an estimated function. So let's consider some estimate function. I don't know what to call this. F arrow. And a set of predictors. So predictors. We'll just call it x. But really what we're talking about is x sub 1 all the way to x sub p. But we're going to call it x. This one is going to yield some prediction. So this is the prediction. And then that function there. And then we put our predictors there. Assume for a moment that both this f tilde and x are fixed. So let's assume that they are fixed, right? So the only variability comes from epsilon. Okay, so here's the mathematical definition of this thing. So if let's assume that these things are fixed. What do we mean by fixed? They're exact. Which in real life, IRL, they're not. So the only variability or something that varies is this epsilon or this unmeasurable variation. And so what does that mean? Well, okay, it is easy to show that this E, okay, I haven't been introduced to this notation in a while. This E y minus y tilde squared is equal, God, it's been a while since I've done stats. I don't know what that E is, if I'm going to be honest. So this thing is so this is the actual correct answer. This is the estimated one. Oh, I'm assuming E is the error. E is the error, I think. I'm not sure. Expected value. Let's see. So I just need to get used to the notation, honestly. So this is the same as the f of x. So the predictors. I'm assuming this one's this one, right? This thing is this thing minus plus this epsilon. Oh, because this is y is equal to this thing. Okay, cool. That okay, we're gonna include this epsilon and then we're gonna subtract it to this thing. Okay, here we're just expanding it. Right. Because this thing is equal to this thing. The estimated function in this, yeah. And then from there, what's gonna happen? Well, oh, so this is the fun part. This actual value minus this thing, we're gonna add the variance to it. The variance of this epsilon. And so from there, we actually get two things. This is what we call the reducible error. This is the irreducible. I think that's important to note, right? Okay, so let's go into the steps here. So this thing actually is the average or expected value. Is the average or expected value of the squared difference between the predicted and actual value. Okay. Of the squared difference between predicted and actual value of y. Yeah, I mean, any of these, even if I switch these, it should still be the same value. So, okay, okay, this is something I might ask GPT to explain this thing. Okay, so here is where I asked GPT to explain what these all mean. Oh God, it's up 140. Okay, once I get through this, I'm gonna stop. Okay, so just like to give context, yes, this is the predicted output y. This is an input x. So that's the true function mapping inputs to output. This epsilon is the random error. So the stuff we can't explain with x, which it also has a mean of 0. And then you have a variance. And so in practice, we don't know what this f is. And so we build an estimate, this one, using the data that we have. So that's what we call data driven, right? We improve this as we plug in more data or as we input more data. Now the prediction error, this is the expected squared prediction error. Okay. And then yeah, I just substitute these things. Oh, so here's the reasoning. This is the reducible error, and it comes from the fact that this might not be exactly f, but it's an estimate, right? How can we reduce this error? How can we make it better and better? Well, we can use better models, more data, stuff like that. Now, irreducible error, this is the noise. So even if we match this and this exactly, we still can't accurately predict because there's some randomness in this epsilon. Yeah, so that's like trying to predict the roll of a die. No model can remove that noise. So that's that external noise. And so the total error is equal to its reducible error plus the irreducible error. That's why ISLR says the irreducible error provides an upper bound on accuracy. You can't break the laws of randomness. Oh, okay, that's interesting. Maybe I'm gonna ask, what does variance mean? Because that's something I haven't touched up on a while. How spread out a set of numbers is around its average. If values are very close to the mean, the variance is small. And if values are far from the mean, variance is large. And then there's a formula for it. Okay, that's the idea. So when we say variance, it's the variety, right? Mm. Okay, so that's something I'm gonna put in my notes. So when we say variance, it's the variety. How can we quantify variety, right? Okay, just to go back to the book, this is the average or expected value of the squared difference between the predicted and actual value of y. And then the variance, so this is the variance of this error term. Epsilon, right? And so the focus of this book is on techniques for estimating f with the aim of reducing the reducible error, reduce, minimizing the reducible error. So it is important to keep in mind that the irreducible error will always provide an upper bound on the accuracy of our prediction for y. This bound is almost always unknown in practice. Cool. Okay, so let's just take a look at what variance is before we end this video. Yeah, so I don't think I have the sufficient prerequisites. I did take a stats course before, but that was like what, like 3 years ago. And I pretty much nah, I remember just in my stats class, I would just like plug in the formulas and then just solve it. But that's what stats is. We're studying data and we can't really there's no exact answer to it. Just like that example that we did, that epsilon, that's something we can control. It just happens to be there. Okay, so here's just like a okay, once I encounter stuff like this, maybe I'll do like a brief review. So a brief review. When we say variance in statistics, variance means how spread out a set of numbers or quantitative data are, how spread out is the data around its average? And so what does that mean? If values or the numbers are quote unquote close to the mean, then that means the variance is quote unquote small. So that's something we can use to quantify how close we are to the average, and vice versa. If the values are large or far, to mean, then we can say variance is bigger. Usually when we're curve fitting, we probably want a small variance. A zero variance means it's perfect, right? And there is a formula for this, which take each value, subtract the mean, so you see how far it is from the average. Hmm. Yeah, so when we're looking at the variance of the epsilon, that's just the average squared size of the noise term epsilon. And so the bigger the variance, the noisier data, right? Which means it's harder to predict. So it's a mathematical way of saying that even if our model is perfect, the randomness itself is unpredictable and its average size is measured by variance, right? So that's the idea. Okay, why not let's just connect it to standard deviation. Yeah, let's just connect it to standard deviation. But actually, before I do that, let me go through the GPT thing. So this is an example of what variance is. So let's say we have some variable z, right? So here we have some variance on this z, which is basically the expected value of the average, this thing, the expected value, no, the value that we got, and then the expected value, right? And then we square that thing. And so that means we take each value of z. Z here is, I don't know. Really depends. Z could just be some number, or it could be like from z1 all the way to some number, z to the n. It really depends on what z we're looking at. But here, let's just make it general. Let's say some z. We take each value of z, or just that value z, subtracted by its mean, and so we'll see how far it is from the average, right? And then we square it. And then we take the average of those squared differences. So if we roll a die, then the mean is from 1 to 6, so that's 7, divided by 2, that's 3.5. And then the difference is from the mean, so that's 1 minus 3.5, 2 minus 2.5, 1 minus 3.5, 2 minus 3.5, 3 minus 3.5, and so on and so forth. We square that, we add it together, and then divide it by 6. And then we get the variance, which is 2.92, right? Okay, now connecting it to standard deviation. So standard deviation, right, let me just put the steps here, just so that, so here we take, I don't know why I wrote it like that, each value of z. So we take each value of z, subtract the mean. So we see how far it is from the average. We square it. And then we take the average of those squared differences. Okay. Then from there, yes. So that's variance. Now we go into standard deviation. And I did remember this in my high school SAS class. It's just a way of connecting it, which is basically the square root of variance. We get the variance, we take the square root of it. Now, what does it mean? So it's just in mathematical terms, the standard deviation of that variable is just the square root of the variance of that variable, right? It's really as simple as that. Now, ooh, why take the square root? If variance is in squared units, let's say if z is measured in meters, variance is in meters squared, right? Standard deviation brings it back to its original units. Mhm. So it's basically, so it tells us, so if variance is how spread out a set of numbers around the average are, this one is what is the typical amount of spread? What is the typical amount of spread in the same units as your data? So like the meters thing, that's what this thing answers, right? Now, if we go back to the, okay, I don't think I put it here. Oh, cool, I didn't. So if we go back to that example, okay, this is just me doing a brief review of my previous stats. So if you look at that epsilon, well, this variance is basically the average squared size of noise, right? And then this one, standard deviation, there is a way to write this in statistical format, which I think it was the cursive O. And then and then the thing that we're getting the standard deviation of is the subscript. And this is basically the typical size of noise. So if that standard deviation is, let's say, equal to 5, then we can think even with a perfect model, predictions typically will be off by about 5 units, simply because of its randomness. Okay, that's just basically the idea, right? So that's the idea of how we can do predictions. Okay, so that's it for this video. I hope you guys enjoyed. I did enjoy personally. I think this is a very interesting topic. And yeah, I also hope you guys learned a lot, and I'll see you all in the next video.